Hello, y'all. Welcome to another video. This is going to be starting off lesson 10 for us, and it's starting module 5 in the ALEKS system here. And maybe just getting started is good. I think I will say one thing. The prior module, I think that was on like exponents and polynomials, right? That was module 4. If we're watching these videos, we're still doing these ALEKS system tests and quizzes and stuff like that. We're going to combine the test of module 4 and module 5 into one test for us. So something to keep in mind for that, just when if you don't see one for module 4. But let's just get to the content here. We're talking about factoring like terms and grouping. So before we get to factoring more complicated things, which would be like things with variables, right? Let's work on factoring just regular old numbers and kind of remind us of how we do that. So one way we can do it is through prime factorization, where we get all the prime numbers that it takes to multiply together in order to get the number you want. So let's factor 12, what it says. Factor 12 through prime factorization. The way we do this is there's probably multiple ways you can get to the same answer, but the idea is you start with just one or two things that multiply together to become 12, your number. And off the bat, top of my head, I see, okay, 6 and 2 multiply together to become 12. And we keep breaking this tree down until we get to only prime numbers, right? A prime number, I can maybe write this. Prime numbers only have 1 and itself as a factor, which is a fancy way of saying you can't break it apart anymore through multiplication, right? So if I look at 2, what are ways I can multiply two numbers to become 2? There's only one way. I can do 2 times 1. That's because it's a prime number, right? 6, on the other hand, I can split further. I can split this to 2 times 3. And since 2 and 3 are both prime numbers, they can't be broken apart anymore. We just got to leave it at this. That is the prime factorization. If I also write this out, the prime factorization of 12 is, and maybe you would put the twos together. I put like 2 squared times 3 as my answer, or I could just leave it as 2 times 2 times 3. Maybe depending on the homework question, might ask you to have it like more concise, like 2 squared times 3, like that. And that is what prime factorization is. Usually that's more useful in certain contexts, though they're both useful in certain contexts, so I shouldn't say that. The t-table is a little different. The t-table are just all possible ways we can factor 12. So you make a t, you put 12 at the top to say we're factoring that number. Okay, so what are the ways I can multiply two numbers and get 12? Well, 1 times 12 is 1. In fact, that's what it is for everything. Prime numbers just have 1 times 12 or 1 times that number. I think we did 6 times 2, so 2 times 6, which works. What I like to do is I like to start at 1 on the left side and then go up in numbers and see like, oh, is 2 a factor of 12? Oh, it is because 2 times 6 is 12. Is 3 a factor of 12? Well, yes, because 3 times 4 is 12. Is 4 a factor of 12? Well, yes, because 4 times 3 is 12, but we've already gotten that set of factors here because 3 times 4, 4 times 3 kind of takes care of it in one row. So it looks like that is all of the factors for 12, like that. And I like this way too. I think this way is actually maybe this way might even be more useful for this lecture, is because it's easier to find the greatest common factor of like a collection of terms here. So when I look at, let's just say, for the number 12, what are all the factors of 12? All factors, if I was to write them all out, is 1, 2, 3, 4, 6, and 12. I got that from the t-table above, right? So those are all the factors here. Um, the greatest common factor would be the largest factor among all terms here. So I'll write that out as well. Greatest common factor. It's the largest factor among all terms I'll say in question here, like that. We often say GCF as an abbreviation. What's the GCF of these two terms, right? And so on and so forth. And the key to this is usually, I think this will end up being easier, the t-table. The key to this is usually knowing all the factors of your numbers or your variables or whatever, so you can figure out what the largest number you can pull out is, what the largest number that is considered a factor is. So let's look at 12 and 8. I'm going to start writing them out. I think it's good to write it out here. Maybe you guys can see what the greatest common factor is already, but I'll put factors of 12. That is, again, 1, 2, 3, 4, 6, and 12. And now let's find the factors of 8, right? Maybe I'll make my t-table here. Well, the factors of 8 are 1 and 8, 2 times 4, 8, 3 times, there's nothing times 3, that becomes 8. 4 times 2 would be the next one, but we already have 4 times 2. Okay, so we have them all. 1, 2, 4, and 8. So we can look at the greatest common factor here as the largest number in both of these lists. What do you know? I have 4 and 4 here. Therefore, my GCF is equal to 4. Not too bad when we're doing numbers. Well, let's do a larger amount of numbers here, and big numbers as well. Now, this is where the t-table might be a little bit tougher, right? Because I don't know if, like, does 14 go into any of these, right? If I just kind of look like, okay, maybe 1 times 72. Okay, 2, I'm a little smarter, so I know that 2 times 36 is 72. 3, 3 times what is 72? That might be tough to figure out. And it might be like a slog to keep going up in numbers one at a time, like, oh, what are all my possible factors? So that's why I like the prime factorization as well, right? Because we can split it up like kind of evenly here and just kind of write all the prime factorization in a row together here. So let's do this. 72, 120, 432. So 72 I already saw is 2 times 36. 2 times 36, so 2 can't be factored anymore. It's 36, I know is a perfect square. That is 6 times 6, right? And I know 6 can be broken up. 2 times 3, 2 times 3, like that. And we can bring 2 down as well. So if I write 72 in terms of its prime factorization, I have it as 2 times 2 times 2 times 3 times 3, like that. Okay, let's do it for all the numbers. 120. Well, I know that is 2 times 60. I know 60 can be broken up in 6 and 10. And I can make this 2, 5, 2, and 3. But your prime trees, your factorization trees might be different from mine, right? I might be doing a little bit different way, but your end result should be the same here. So 120 is equal to 2 times 2 times 3 times 5. Here. Okay. And then lastly, let's do 432. 432 is tough. I don't know 432, a lot of factors for 432, but I know it's even, so I know I can multiply it by 2. 2 times what is 432? You can get a calculator. Using a calculator is fine, right? Or going online for a calculator or whatever. I can kind of already see it's 2 times 216. And I also see, sorry, my dog's making some noise here. Give me 1 second. So I know 216 is also a even number. So I can split this up into 2 times, what is this, 108? And again, 108 is also an even number. So I can split this into 2 times, man, I'm working on my algebra or my arithmetic here. Was that 54? Also an even number. So this is split into 2 times 27. Okay, and there we go. This is 3 times 9 and 3 times 3. Okay, well, sometimes that happens, right? What do we have? We have a 2, another 2, another 2, another 2, and a 3 here. So 2 times 2 times 2 times 2 times 3 times 2 times 2 times 3. So 432. 432 is equal to 2 times 2 times 2 times 2 times 3 times 3 times 3. Okay, now I want to find the greatest common factor. You might be like, okay, well, look, there's 3. 3 is the greatest common factor because it's the largest number they all share. That's not exactly true, right? The greatest common factor when we do these prime factorizations is going to be the combined numbers we all share. So they all share a 2, right? They all share another 2, and they all share, it looks like they share a 3. So the greatest common factor, um, oh, actually, I also made this mistake here. This is also another 2 as well. So let me move this over. So we have another 2 times this. I thought I was missing a 2 here. That's why, oh, and this is a great example. This is why I like to put an arrow down to like the straggling numbers that are prime that are like high on our tree here. That way, when I write the whole entire thing out, I can see all the things in my factor. So I just missed that 2 there. Okay, whatever, right? Either way, what are my shared factors? I have 2, a shared factor, 2 is another shared factor, 2 is another shared factor, and 3 is a shared factor. 432 has an extra 2, but we can't include them. What's the GCF here? Maybe I'll write it over here. GCF. The greatest common factor is the multiplied version of all those common factors, those common prime factors. So 2 times 2 times 2 times 3, which is 8 times 3 or 24, if you were to combine that together. That is the true answer. Now, it is very tough for me to see that these 2 numbers, all 3 of these numbers, have a factor of 24. Like if I was to do the t-table, 24, what, times 3 is a t-table? We're 120, 24 times, it's a little tougher to see, 432 especially. So sometimes these prime factorizations are good. Okay, how about when we find the GCF with variables? Well, it's the same process we were just doing. We need the GCF of the numbers in the problem. And then what we do is we just grab the lowest power of each variable, like need the lowest power of each variable, right? And it might seem like, well, how does that work for the lowest power? But let's try some examples first. I have 6m to the fourth, 9m squared, and 12m to the fifth. So I can still do the same stuff I've been doing before with the numbers. 6 can factor to 2 times 3. 9 can factor into 3 times 3. And 12 can factor into what? 4 times 3 and 2 times 2. Okay, that's not too bad. So how do I write 6m to the fourth as broken up as possible as a sum of its or the multiplication of all its factored stuff? I can write it as 2 times 3 times m times m times m times m for 4m. So right, when in doubt, write it out. What about 9m squared? 9m squared is equal to 3 times 3 times, and then writing it out, m times m. And then lastly, 12m to the fifth is equal to 2 times 2 times 3 times, and then I write 5m's here. Okay, now let's highlight the things that are matching. It looks like they don't all share a 2 because 9m squared, that 9 doesn't have a 2 there, but they all share a 3 in each line. And I have an m, a couple of m's they all share as well. This is exactly, so the GCF here is going to be 3 because they all share 3 times m because they all share an m times m because they all share another m, or 3m squared. Like so. You don't have to do this stuff if you don't want to. Sometimes on the beginning part, it's like nice to just like to what's it called? Write it out here. So I'll do it one more time for this. I have negative 12 p to the fifth and negative 18 q to the fourth times p. All right. Well, we first do the numbers part. So I look at 12, which I already have above, 4 times 3, 2 times 2. And I look at 18, which is what, 2 times 9 and 3 times 3, right? Yeah, yeah. 18 is 2 times 9. That 9 can break up even further. So I have those are my prime factorizations here. So let's write this out. Negative 12 p to the fifth is equal to, well, I see a negative there. I did not do any negative numbers on my like prime factorization, but I can include a negative, like a negative 1 as like its own little factor. So that's like another extra rule here. If your number is negative, you can add a negative 1 as a factor times your prime factorization. And then times p times p times p times p times p. And let's do the same thing for negative 18, 2 to the fourth, p, which is negative 1 times my 18 prime factorization times 3. Let's like change these colors to blue here, and I'll change these to red because it's like a special case here. So just remember those there, right? Times q times q times q times q times p. Okay, so let's look at this, I guess, prime factorization of these terms, and let's see if we can find the greatest common factor. Well, what's being shared here? A negative 1 is shared, a 2 is shared, a 3 is shared, and it looks like a p is shared there. Um, the top one has a lot of p's, the bottom one has a lot of q's, but those aren't shared here. So those together become what? GCF is equal to negative 1 times 2 times 3 times p, or negative 6p. It's by GCF. Now, I would pause the video and look at these two problems and be like, can I see that I can kind of like factor out a 3m squared out of everything here? I think that's the biggest thing I can factor out. And same for this one, for negative 6p. Can I factor out my a 6p or negative 6p out of everything? Well, I can factor out a negative. I can like both 6 is a factor of 12 and 18, and I can pull out a p as well. That is the idea of what this next point is, which is reverse distributing here. So we're going to try to do these problems together as well. Reverse distributing, which has to do with factoring at the end of the day anyways, right? So let's look. What is distributing? Let's remember that from like a video or two ago. Distributing. Well, when I have something like 3 times x plus 6, what can I do? I can distribute that 3 back into like the parentheses, and I get what? 3x plus 18. Booyah, right? Nothing bad. What if I reverse this process though? Reverse distributing. Well, that's really like if I started with 3x plus 18 and I rewrote this kind of like before, it's as if I see these all both have a 3 attached to it. I can rewrite this as 3 times x plus 3 times 6, right? If I imagine myself pulling that 3 back out so that x plus 6 is in a parentheses, I can move this to be 3 times x plus 6. And isn't that the same thing as this prior step? If I move this back out, it's as if in the future step, I can distribute it back in. This is the reverse distributing point, which is also the same as what we call factoring out a 3 here. You can factor out your greatest common factor and leave everything else on the inside. That usually helps because then we've kind of broken this up to where we have something we know and then something simpler in the parentheses. And sometimes, depending on the context, that is useful for us. This was the GCF times what's left. That is what I created. Reverse distributing is starting with this and taking the GCF and what we call factoring out in a reverse distributing form. Okay, so So let's try this. Let's factor 4x squared plus 6x. Again, the idea is we can create like the prime factorization of both of them. Maybe you can see it already, right? But what can 4x squared be built out of? It's built out of 2 times 2 times x times x. 6x is 2 times 3 times x, right? So this is the prime factorization of both. And I see that they share a 2x out of both of them. Well, look at what ends up happening. If I factor out this 2x, right? I'll leave it as black here. What is left in this first term? Well, I factored out this, so I don't have that 2x anymore. What is left is the stuff that's not highlighted. So 2x plus, I factored out this stuff. What is left is a 3. And notice, this might look like, man, what did we really do here? Where did this stuff come from? Let's kind of reverse this step. Let's go backwards. Get back to the beginning. Let's distribute this back in. What is 2x times 2x? 4x squared. What is 2x times 3? 6x. So I have reverse distributed a 2x, or I have factored a 2x out of these two terms. And these two things might be easier to work with in the future. That's the motivation here. So let's keep on going here. Let's see if we can do this without pulling all the numbers out, right? I have a big parenthesis thing, and I should have a greatest common factor on this here. So maybe you should pause the video and think, what is the greatest common factor I can pull out of these three numbers? Right? You can write it all out if you want. You can do the prime factorization of them all, but maybe you can see these are all multiples of 4. They're not going to be multiples of 8 because 12 isn't going to 8, right? So it looks like 4 is our biggest number we can pull out. How many of my variables can I pull out? Well, I see a p to the fifth, p to the sixth, p to the fourth. I can pull out of all of them, I can pull out a p to the fourth here. And then lastly, for my q's, I can pull out, there's a q squared, a q to the third, q to the fourth. I can pull out a q squared. Notice what happened on this factoring. The GCF, when the variables are involved, are the lowest power of the variable. What were the lowest powers in this problem? I had a fourth power for the p, so I pulled out a fourth power. I had a second power for the q's. I pulled out a second power. So I'm still consistent with the rules that I made, or like the guidance I gave at the beginning of this here, right? Okay, so we have factored all of these out. Imagine I took my 4p to the fourth q squared out. What is left on each of these terms? Well, on the first one, I am left with a 2p, just 2p, it looks like, because I have taken out all of my q's. I've taken out all but 4. I've taken out 4 of my p's, and I have a 2 remaining. If I distribute this back into this first term, I'm going to have 4 times 2 is 8, p to the fifth, q squared. That's exactly what this is. Now, what's my next term? Well, I pulled out a 4, which means I should have, if I distribute this 4 back in, 4 times 4 is 16, so I still have a 4 inside the parentheses. How many p's do I still have in my parentheses for this term? Well, I pulled 4 of these p's out. That means there's 2 p's remaining. And I pulled 2 q's of these out, which means there's 1 q remaining. We still have this minus here, so we'll leave it like that. Minus, what's going to be the number here? Well, I pulled out a 4 of the 12. What's remaining? A 3. I pulled out a 4 out of the p's, so I put 4 p's out, so there's no p's left. That's fine. And I have 4 q's there, but I pulled out 2, so I have 2, or q squared here, like that. So that could have been like confusing for you. If you write it out like what I just did here, you'll end up getting this same answer, and the remaining stuff on these factors will be these terms. If that's how you do it, that's how you do it. It takes more work, but that's okay. It's okay to take more work if you get the right answers. Right? Okay, so this is a little bit of I'll say special case, where when we're doing factors of fractions, I know fractions are scary. The way we should do it is take the greatest factor of the numerators, the greatest factor of the denominators, and then do the same with the b's here. So what is the greatest factor of the numerators? Well, they have a 1 and a 2. The greatest thing that they both share is a 1, right? If I wrote 1, 1 is just equal to 1 times 1, I guess. And 2 is equal to 2 times 1. I guess maybe I wouldn't even do 1 times 1. It's just 1. And then 2 times 1 is like the best we got here. So they only share a 1. That's the greatest common factor. When the numbers are the same, the greatest common factor that is shared is a 3, is the same number. So I have, this is the greatest common factor at the top, greatest common factor at the bottom. How many factors of b do we have? Just the 1. So I'm going to have b minus, ooh, what's left here? 2, it looks like. How did I get that? Well, let's distribute this back in. 1/3 b times b becomes 1/3 b squared. 1/3 b times 2 becomes 2/3 b. And there we go. This is why it's sometimes nice. I've kind of like pulled this fraction to the side, and now I have things I can maybe work with in later problems as well here. Okay, so again, just remembering, I'll say like for fractions, factor like this. GCF of the numerator over the GCF of the denominator. And okay, let's look at what we have here. All right, so we'll do these last two problems here, like this, where we're factoring out an entire term from both groups. Sometimes it might seem like a little weird to do this, but remember, when we're on multiplication, these things I'm considering as one term. These things I'm considering at one term, kind of like how we have a mixture of numbers and variables. This is all like one term I can factor something out. So even though I have like a parentheses here, this is a shared factor among both of these terms here. It's kind of like if I have, let's write it like this, like a times, um, let's just put the word smile. Why not? Plus 4 times, and let's put the word smile. If I wanted to factor out, they both have the smile as a common factor. So I can pull both of these smiles out and kind of like a reverse distributing form to get smile times, what's the stuff on the inside? There's an A on the inside and 4 on the inside. A plus 4. If I distribute this back, don't you see how I get the same thing again? It's going to be the same case here. If I distribute or reverse distribute this a plus 3, that's like a same common thing. They look the exact same. So I can reverse distribute this, and I'm left with a plus 3 on the outside times, right? That is what this is here. That is times a plus 4, like that. So you can factor out an entire term. Like this is all one term, but you can look at each of these individual things we're multiplying by as also a term. Kind of like terms is like very loose term. Loose term, right? That's funny. Um, but we can factor an entire parentheses of stuff out of the original things here. And when we do that, we're left with a plus 3 times a times 4. That looks a little weird, right? But it's something we can do, just like we can do it for smile, just like I can do it for a symbol. If this was a stick figure, right? I can factor out a stick figure, and I have a stick figure on the left side, like this. That is factored out. Because when I distribute it, I'm back to here. When I distribute this entire parenthesis to both, it gets exactly that. Okay, same idea for this one. Here, I have common factors that I can pull out of both of them. I'm not doing greatest common factor stuff anymore. I'm just kind of seeing that these are two common factors I can pull out in a reverse distributing form. So I pull that out to get x plus 1 on the outside, like that. What is left on the inside? Well, on this first term, I had an x squared. Minus, on the second term, I had a 5. So minus 5. This still works if I had x squared times 7. I'll put a 7 here. Minus 5 times 7. The reverse distributing or the factoring of this would literally be pulling that 7 out, factoring that 7 out, times x cubed minus 5. Yes. So that's how you do, or I don't know why I had x cubed. I should have made this as x squared, my bad. Like that. So it's the same problem as before. Okay, so I think we'll stop there in terms of this video. Stay tuned for the next video finishing this lesson and have a wonderful day.